Hello, and welcome to Living Proof, the Isaac Newton Institute podcast. My name is Dan Aspel. In this episode, I'll be speaking to Professors Lionel Mason and Maciej Dunajski of the Twistor Theory programme. They'll be speaking in depth about the scale and challenges of this far-reaching topic that, amongst other things, aims to unify general relativity and quantum mechanics. We hope you enjoy the episode. So welcome to Living Proof. I'm joined by two guests today. On my left is Lionel Mason.
So I'm Lionel Mason from the University of Oxford, Professor of Mathematics.
Fantastic, thank you. And also we have Maciej Dunajski.
I'm Maciej Dunajski. I'm a Professor of Mathematical Physics here at the University of Cambridge.
Excellent. So we're here today because you are two-thirds of the organisers of the Twistor Theory programme. And I'm going to read the first sort of couple of sentences of your programme description because that's what grabbed my attention, at least, immediately upon learning about your programme. And that begins with, Twistor Theory was originally proposed by Roger Penrose as a new geometric framework for physics that aims to unify general relativity and quantum mechanics. In the Twistor approach, space-time is secondary, with events being derived objects that correspond to compact holomorphic curves in a complex threefold, the Twistor space. So that strikes me as very, very interesting and ambitious. You've mentioned some major theories about how we understand the universe there. Am I right to be as excited as all of this about your programme?
Well, I have been excited about this programme, I'm perhaps embarrassed to say, for 40 years, but it is unfulfilled. So this is something that Roger Penrose first introduced, probably in his own mind, more than 60 years ago, and publication just a bit less. It's never quite had the presence in the minds of theoretical physicists that other approaches like string theory or loop quantum gravity and so on, and holography have had. But to my mind, it's always appeared to be potentially deeper than any of those.
It is Roger Penrose's creation. In some sense, it goes back as a mathematical theory to some of the nicest mathematics of 19th centuries, of geometry, very pictorial. But as far as physics goes, it might be the most non-orthodox way of thinking about physics, because unlike most, if not all, of these other modern theories, it gives up on the idea of space-time point as an elementary building block. Right? All the theories, including string theory, would still think of space-time as consists of points, whereas in the Twistor approach, it appears that light rays are more fundamental than points, and points are derived objects. And the hope is that if you think of this theory in the right way and bring in quantization, then at the quantum level, points will be some fuzzy objects, not points anymore, and that will shed light on what quantum gravity is.
But I should say that this programme has focused perhaps more on the mathematical impacts. At least, well, you're somewhere in the middle perhaps, Maciej. But Katerina was very much a pure mathematician, I think, and not much interested in physics. And in fact, although you describe yourself as a professor of mathematical physics and I describe myself as a professor of mathematics, I think I'm probably more interested in the physics than you are. But anyway, I think one of the hallmarks of the subject is that it's mathematically has impacts across certainly geometry, representation theory, group theory, but it's still not quite there in the physics. But it's getting there, and recent years have been just as exciting. So I would say that the last 20 years have been quite exciting for me as far as the physics is concerned, but I can't yet say that we have the same maturity of approach and theory as, for example, the string theorists. Although we've got incredibly, much further than we were 20 years ago by virtue of talking to string theorists and learning from them. I mean, we've managed to really up our game by doing so.
Yeah, it's worth mentioning actually that this is, as we record this, is the final day of your month-long program here at the Newton Institute. We're sitting in the main seminar room at the moment. Those with sharp ears might be able to tell from the acoustics. This is, in the case of all of these kinds of research programs, it's a rare opportunity, isn't it, to spend so much time with your peers, focusing on the questions involved here. And I believe you've had Roger Penrose's involvement as well.
That's right. And, retrospectively, we think it would have been a good idea to have a 6-month-long program. We had lots of very good people who gave lectures, and we were overwhelmed by these excellent lectures, but it would have been even nicer to be able to talk more to each other. Many of us have collaborated, finished papers because of the I&I involvement, but for me, or for us as organizers, I think it's fair to say that the program has just been full of exciting talks, which I think is what the 1 month programs tend to be like, as opposed to the longer programs. But indeed, we had Roger Penrose who came for a day, and he gave a talk which was advertised as a general public lecture. It was at the end technical. Roger still has some brilliant ideas about where the theory should be going, but he's told us about the history of the subject as he saw it.
Is it possible to identify I think you said around 60 years is the timescale of this modern thought on Twistor
Yes,
theory?
Sorry, I'm saying this just after talking to Roger, that he first thought of this after the Kennedy assassination.
Wow.
Driving back from Dallas with a silent colleague. But anyway, sorry, that's
an incredible detail.
Yes, that's right. But it was first published, I guess, in '67, and already then that first paper is very mathematical. You could see that it had its origins in very deep mathematics, that it itself was going back to the 19th century. Sophistry and Klein and whatever.
You see, the interesting thing was Roger, trained before he became world famous physicist. He trained here in Cambridge as a mathematician, so he knew sort of what we now call algebraic or projective geometry, the branches of mathematics a physicist would not have been exposed to. And when his interest shifted under the influence of Denis Sciama into physics, he kept this knowledge of geometry together with his genius, which allowed him to come up with Twistor theory. But although it's a mathematical paper, as Lionel says, I don't think back then Roger was aiming to solve any profound mathematical problems. His interest was in physics. But it so happened that in the next decade or so, the Twistor theory had these spin-offs in the pure mathematics direction. So when Roger moved to Oxford, his group interacted with that of Michael Atiyah, and it turned out that Twistor is a wonderful tool to solve problems which pure mathematicians did not know how to solve. So I think the majority of the participants of this program, or at least a half, are really pure mathematicians with their pure maths agendas, and not as big an interest in physics as two of us might have.
How did that feel for the two of you?
Well, I'm somebody who's very easily distracted. I self-diagnose as ADHD, and so I love talking to the pure mathematicians as well as to the physicists, and I'm fascinated by mathematical structure as much as I am by trying to get to grips with the physics.
Well, it's the same with me. At some level, distinction between mathematics and theoretical mathematical physics is a social one. If you look deeper into what physicists are doing, it's not necessarily physics which you yet see in big accelerators, but there is this kind of share of common ideas, and I think for all approaches represented at this program, it's this presence of complex numbers, which in Roger's view is very essential to be incorporated into physics, and geometry. So it's a very geometric approach, and it's not always easy to find a common language with all the participants. I mean, the two of us can just about do that, but there would have been some participants who would have to try hard to communicate with each other. But they did try, and so some interesting collaborations came out of this.
It strikes me that must. I mean, it's clear that it's excited you and that there's been sort of progress made through these collaborations, but at any point did you feel yourself thinking, wouldn't life be simpler if we were all from the same school of thought and we were all working on a problem which we all agree on and understand? That sort of mingling of people from different disciplines can be challenging, I imagine.
Well, it's difficult to keep track of the details of all of each other's ideas. I mean, people from different walks of life, mathematical life, of course, here, have very different languages. So one of the hardest problems is to actually understand each other's languages. But on the other hand, people like me, I'm just fascinated to sort of make connections, but it can be distracting. So you don't know which of your many ideas you've had are actually going to be either profound or realizable, and so this sort of program sort of raises many projects, but then you need time to go away and actually think about them.
And also, a lot of it maybe is about the language. So it's often you'd hear a physicist saying, let's multiply x by 7. And the mathematician will say, well, let's choose a trivialization for a line bundle, which wouldn't mean a lot to a physicist. But when they sit and talk to each other, they'll agree that they're talking about the same thing. So part of this program was to allow people to, to start understanding each other and what it is they're doing.
I think every single group of organisers that I've ever spoken to at the Newton Institute has said a similar thing about the sort of linguistic challenges between different groups, physicists, mathematicians, different schools of mathematicians, to the extent where it seems like having a programme to create a universal translator across mathematics might be
the Babelfish.
Yeah, exactly. Yeah.
That would be a dream device for mathematicians.
Do you feel like you made sort of good progress in that sense throughout this? Is it now, for your community at least, is it resolved, or is it there's a pathway to communicating better?
It hits different generations differently, and the language is so localized to each group people are in, and So I've been to, I'm old and so on, and so I've got quite a lot of experience of trying to understand people from different groups. But I'm sure it's a complete, it's this Babel's Tower for a graduate student sort of.
Now, a good thing was that people came to each other's talks and they did ask questions, trying to articulate them the best they could, and there were answers. So it was, we have tried before. It's not the first Twistor meeting which aimed to bring two or more than two, as in this case, communities together. But I felt that we might have had a bit more luck this time than we did in the past.
It may just be that you're growing older and you're understanding more of other people's languages.
That's correct.
And we've mentioned about the sort of history of this field and how Roger Penrose, major figure within it. Is it possible to identify sort of certain moments over the lifespan of this field where more progress has been made, sort of accelerated periods? And if so, was this meeting one of them?
Well, I mean, it's easy to point to times in the past when progress was accelerated. So I would, the 70s must have been truly exciting, I think, with, Roger Penrose's. There's a so-called nonlinear graviton construction which encapsulates half of gravity into one of these deformed twistor spaces, and then it was applied to gauge theories and massless fields, and extended to representation theory in pure maths, and there's a great flowering following that. But there was a strong feeling that as far as physics was concerned, it was stuck, and that was already the case when I first arrived in the early 80s. Even by the early 80s, there's a strong sense that the physical program was up against a brick wall. And that remained in my mind for 20 years. And both Maciej and I went off in what you might call a more mathematical direction. So we both went off studying applications of Twistor theory to nonlinear problems in physics, geometry and physics, but were not really core problems, I think it's fair to say. So it's fun to solve them, and there are plenty of people out there who regarded it as their life's work to solve such problems, but it wasn't sort of necessarily progressing the Twistor program.
So going back to more 70s history, one thing which Roger recalls as a breakthrough moment, it was when he moved to Oxford and started talking to Michael Atiyah, who is now passed away, but he was very good at bringing people together. And back then, Roger and his group, they had a way of, technically speaking, solving some linear differential equations by integration. It was not clear what was being integrated, and it was Michael who explained to Roger that there's this technique in fairly advanced mathematics called cohomology, and that's what they were doing. And I think that was really a moment where Oxford physicists and mathematicians started talking together, which then led to progress in pure mathematics. So that's one big date. Then in late 80s, maybe mid 80s, just before my time, but in Lionel's time, it was realized, was a former student of Roger, Richard Ward, realized that almost all, if not all, equations which we now call integrable. An integrable equation is something opposite to chaotic. These are equations which you know how to solve in principle analytically, and they're very mysterious until this day. But it was pointed out that all these equations have a Twistor description. So this was not quite doing physics, but maybe that brought applied mathematicians to the subject. So far we had theoretical physicists and pure mathematicians, but now Twistor started telling you how solitons move. And so that really influenced my own research in a decade later. So that would be another breakthrough moment in the theory. And then Lionel was alluding to things changed in 2003, 2004, where Edward Witten pointed out how Twistor theory ideas can be used in string theory and computing perturbative scattering amplitudes. And Lionel is the prime, if not the only example of the old school Twistor theorists who took it on board and made great progress with it.
Yeah, so I mean, I'm not sure whether I should talk about the politics of the subject, but Roger makes no secret of the fact that he disapproved of string theory and supersymmetry and so on. And but Ed Witten was creative enough to say, what happens if you put a string theory inside Twistor space? And in doing so, he discovered that you could, when I was talking about the breakthroughs of the 1970s, Roger Penrose and Richard Ward discovered how to deal with the left-handed particle gravity. And what Ed Witten observed was that if you put a string theory into Twistor space, the larger strings, the tiny little strings, they just see the left-handed part of the theory. But then if you have big strings, they could actually sort of tell you about that they completely naturally gave you the scattering amplitudes for the full theory, and that to me at the time was just so boggling that this was how to make twistors. This was a way to make twistors physically relevant in complete mathematical naturality. We were only ever looking at these curves of degree 1, and if you just went up to degree 2, 3, 4, 5, up to infinity, you'd get all these extra contributions that would add up to the full theory. And anyway, so since then, it's looked a bit more promising to be able to actually have it as a foundational approach to physics. But I think really coming to grips with what people modern day physicists understand as quantum field theory is still a challenge, and I think we still have a lot to learn.
One question that this element of our conversation raises is what sort of applications would one expect from twistor theory, or has one seen from it?
Well, so this is application is a broad theme, but there are many applications and many to come in pure mathematics, and this is just how people now do their calculations. I mean, there are problems we've been discussing earlier today in four-dimensional geometry, which we hope to solve using twistors, and if we won't, then somebody else will, and there'll be applications in representation theory, which is another area of pure mathematics, more kind of mind-catching applications, which you might think they could be real-world applications. They have to do with inverse problems. So this is another part of pure mathematics which benefited from twistors, is how to sort of reconstruct an image from the boundary, or from the set of X-rays hitting the boundary. And this, if you look at this mathematically, it ends up being the sort of problem twistors are made for. So that there is a group of researchers, they were actually not represented at this meeting, who look at these inverse problems to do with invisibility cloaks using twistor-like techniques. But of course, for Lionel and colleagues, the big question is what will be the applications in physics, and I think it's still an open verdict, although indeed this right-handed part of gravity which evaded the early twistors is now being incorporated, but it's being incorporated in what we call perturbative sense. So you have to allow yourself to say that if a number x is small, I can take a complicated function of x and make it much simpler, and that has worked for us for the last 100 years in conventional quantum field theory. But it's not certain that it has to work. But this series which you obtain in these things are make any mathematical sense. So it'll be very interesting to see what will happen the next decade with these calculations.
I mean, even if you're so I think Maciej is expressing some dissatisfaction in expressing this as a series, but getting that series right is still a challenge, in the sense of in quantum field theory there are always loop corrections, and I think we're fairly comfortable with some of them up to 2 loops, but you'd really like to have a framework where you believe it's happening forever, and it's not just something where, if I fiddle a bit, I can make it work. 2 loops. Well, you got 3, you got 4, and there's plenty more numbers larger than 4 and 5 that you could hope to get it right for. So you want something systematic, and I guess the string theorists claim to have that. We don't, and the other actually nice connection with what Maciej was saying was a completely different story. So he was talking about sort of inverse problems, maybe from picking up things from the boundary and rebuilding what's the interior from what's on the boundary of a system. And in physics, this has become an independent program of its own. So it comes under the name of holography, because a holograph is a 2-dimensional representation. It encodes in 2 dimensions a 3-dimensional structure, and gives you can reconstruct the 3-dimensional structure from the hologram. So holography has been this huge program which sprang out of string theory 25 years ago. Names Maldacena and Witten associated with it, and it's now virtually become its own subject. Partly because the Maldacena conjecture tells you that quantum gravity, which is notoriously hard to deal with, can be encoded in a simpler theory on the boundary. And one of the things that we've been learning over the last few years now is that twistor theory bonds very, very naturally with that program. So we've had this big insight from strings sort of 20 years ago, and I guess there's some considerable optimism at the moment that there will be another burst of new ideas and so on coming from the interactions with holography. So we're part of a celestial holography. Some of us here at this program are part of a celestial holography Simon's collaboration, which is aiming to do that.
So one of the technical problems with this holography, as it was 25 years ago, is that it required the space-time to have a cosmological constant of a wrong sign. So we now know that that the universe is expanding, in fact, in an accelerating way, which requires this constant to be a very small but a positive number. Well, holography, as it was conceived, works if the cosmological constant is a negative number. So it can't, at some level, it cannot be right as theory of physics. And I understand this new Twistor techniques and approach will allow for this cosmological constant maybe not to be positive, but to be zero. And that will be a great progress. Is that a fair statement?
Yes, I mean, I think, well, so these things are still speculative. I think it's controversial that the Maldacena-Witten holography can be made to work with zero or positive cosmological constant, but the attempts that people have had so far just drove straight into twistors. People started following the algorithms that they're used to using and constructing some algorithms. And the first thing that they discovered 3 or 4 years ago were some twistor structures. So that's been very exciting for us to see that they tie in so neatly.
Well, thank you both very much for that insight into the scope and breadth of this program. It was very satisfying, Maciej, when you were describing the pure fields which the applications are present in. You more or less listed 5 or 6 different programs which INI has run over the past 5 years or so. So it all ties together beautifully. And also, thank you very much for mentioning Michael Atiyah, who was, of course, the inaugural director of INI at the start of the 90s when it was first opened. So that's a nice connection with what we do here as well. So thank you very much for your time. I think that's a good amount of insight for us to take on board, and I'm sure everyone listening has been absolutely fascinated by that. I'm going to finish by just asking a sort of more human, personal question. As it's the last day of the programme, how do you both feel about what's happened here over the last month?
Well, I can't deny saying that I'm tired. I did cycle in every day. I live outside Cambridge, but it's been a great program. I focused on collaborating with 2 or 3 people, and some of whom are my long-term collaborators. So I had all done. I've benefited myself, but I've also learned a lot. And I hear from especially younger people, they've learned a lot too, and they started, writing papers together. So it's been very good. I mean, in some part of me thinks, could it be longer? But on the other hand, both Lionel and I have day jobs to get on with, so perhaps not. Maybe next time.
I mean, just to add to that, I mean, it's been fun for me. At Maciej and I haven't written a paper for 24 years, and maybe we're just about to write one.
Well, it's not. That's not exactly right.
Oh no, sorry. We wrote the one with Michael Atiyah.
We did actually write the paper together with Michael Atiyah about the history of Twistor Theory. So this was back when Twistor Theory was approaching 50th anniversary, so and we had a review of the subject.
Yes,
that's right. So, but now we're collaborating on what I think is a very exciting project.
Yeah, so that's been fun for me to go back to working with Maciej, which I hadn't done for a while. But for me, otherwise, I think I've just been making lists of fun projects and wishing I had more research students to give them to.
And final question, which I should have asked at the beginning: how long have the two of you worked together? When did you first start?
Well, I can answer that. So I was Lionel's PhD student, and I started in '95. So this is it'll be 30 years next year.
Excellent. Well, let's hope let's hope for the same again.
Yeah.
Excellent. Well, thank you both very much.
Thank you.
Thank you.